Welcome back to our series of lectures on radiation physics. In our previous video, we saw how the X-ray photon was born in an X-ray tube in a diagnostic X-ray machine or in a linear accelerator. Today we are going to explore the physics of X-ray photon treatment beam. We will cover three important topics that form the absolute foundation of your clinical dosimetry. First, we will deeply examine the concept of beam attenuation. We need to understand exactly how and why the X-ray photon beam gets weaker as it travels deep into the patient. We will look at three specific fates of an individual photon, which are transmission, absorption, and scattering. We will also learn how we use attenuation coefficients to measure this exact rate of removal of these photons when an X-ray beam enters tissue or matter. Second, we will discuss the penetrating power of an X-ray photon beam. We will learn how to accurately measure this beam quality using the half value layer, which we simply call HVL. Finally, we will explore a very interesting phenomena called beam hardening. Because our clinical beams contain a mixed spectrum of energies, the patient's tissue will naturally filter out the weaker photons. This filtering leaves behind a much harder and highly penetrating beam. Mastering this physics of X-ray photon treatment beam is your first major step in understanding accurate dose delivery. Let us begin. Let us start with the very first and the very core concept called beam attenuation. Beam attenuation. Attenuation in English means is the reduction in the force or intensity of something. We must understand exactly how our treatment beam behaves inside the patient. Imagine shining a bright flashlight into a very thick wall of fog. As the light travels deep into the fog, it gets dimmer and weaker. The fog is literally blocking and removing the light. In our clinic, the exact same thing happens to our treatment beam. When an X-ray photon beam enters a patient's body, its overall intensity is gradually reduced. It gets weaker and weaker as it travels deeper into the body. This gradual weakening and reduction in the number of photons is what we call beam attenuation. Beam attenuation. How does a treatment beam look like? Remember that the treatment beam is not a continuous, unbroken laser like this. Instead, it is a massive stream of billions of tiny, invisible packets of energy called photons. When this massive stream of photons enter tissue, three fundamental events can happen. Let us see them one by one. This is a matter, suppose a body tissue. It is made up of atoms. Let us see what happens when an X-ray photon enters the body tissue and passes through these atoms. There are three possible fates of an incoming photon when it passes through the body. Photon will suffer one of them. Keep looking on the screen. First possible fate of a photon is photon can undergo transmission. Here, this photon is very lucky. It travels perfectly straight through the tissue without interacting with any atom of the tissue. It exits the other side completely unharmed and unaffected. it continues to retain its 100% energy. Second possible fate of this photon is it can undergo absorption. Here, the photon is not so lucky. It crashes directly into a tissue atom and gives up all its energy. See here. It deposits 100% of its energy right there, completely disappears and ceases to exist. Third possible fate of a photon is this photon may undergo scattering. Here, this photon interacts with an atom and bounces off like a billiard ball. Once again, here this photon interacts with an atom and bounces off like a billiard ball. It loses a little bit of energy and flies away in a completely new direction, like this. Because it was deflected off its straight path, it is considered removed from the primary beam. I want to show you these three possible fates of an X-ray photon again. The first thing that can happen to an X-ray photon entering the body is transmission. See here. This blue is the X-ray photon. These golden balls are the atoms of a tissue. In this, the X-ray photon travels perfectly straight through the patient's tissue, like this. It avoids all atomic collisions completely. There is absolutely zero interaction with the atoms of the tissue. As a result, this photon exits the patients completely unharmed and unaffected. It successfully reaches our radiation detector on the other side. Second thing that this photon can suffer is absorption. We call this process absorption. See here. This blue color is the X-ray photon entering the tissue. These golden balls are the atoms of this tissue. Here you can see that a photon has crashed directly onto this atom inside the patient's tissue. During this crash, the photon gives up 100% of its energy. It transfers all of its energy to the tissue immediately. Because it has lost all its energy, the photon completely disappears. It simply ceases to exist. It has been completely removed from our treatment beam. Finally, this is another thing which can happen to this photon when it is traveling through the body tissue. This is the third possible fate of this photon. This is known as scattering. See here. The blue color is the incoming X-ray photon. The golden colored ball is the atom of the tissue. Here, the incident photon interacts with the tissue atom, but instead of disappearing, it bounces off the atom like a billiard ball. It bounces off the atom like a billiard ball. During this deflection, the photon loses only a partial amount of its energy. It survives the crash, but it flies away in a completely new direction, like this. Because its path was altered, it completely misses the tumor target. Therefore, we consider this scattered photon to be removed from our primary beam. I am going to show you all three possible fates of a photon when it passes through the body tissue on this one slide to summarize it. We must understand exactly what happens to our treatment beam within the tissue. See here. These black colored dots are the atom of the tissues. Remember that the X-ray photon beam is a massive stream of individual packets of energy called photons. This is one of those photons entering the body. When this massive stream of photons enter human tissue, every single photon faces one of the three immediate fates. The first possible fate is called transmission. This photon travels perfectly straight without interacting with any atom. It exits the tissue completely unharmed and unaffected. The second possible fate is called absorption. This photon crashes directly into a tissue atom. It gives up all of its energy right there. It completely disappears and ceases to exist. The third possible fate is called scattering. This photon bounces off an atom inside the patient. It loses some energy and flies away in a completely new direction. Understanding these three specific events is the absolute key to mastering medical physics. I hope you are clear now about what all can happen to the photon when it enters body tissue. Now, let us look at the complete picture on your screen and try to define beam attenuation. We have discussed the three possible fates of our X-ray photons. We must now clearly define what we mean by beam attenuation. This is a very important definition for your exam and clinical practice. Look at the simple visual equation on this slide. If a photon crashes into an atom and completely disappears, it is successfully removed from the beam. We call this physical process absorption, like this. If a photon bounces off an atom and flies away in a new direction, it completely misses our tumor target. Because it is deflected off its straight path, it is also considered removed from our primary beam. We call this physical process scattering. Therefore, beam attenuation is strictly defined as the combination of absorption and scattering. Once again, beam attenuation is strictly defined as the combination of absorption and scattering. It is simply the physical removal of photons from the primary treatment beam. Remember that the lucky photons that travel straight through are transmitted. They are neither absorbed nor scattered. That means they are not attenuated. They are transmitted. Transmission is the exact opposite of attenuation. Beam attenuation only includes the photons that are physically removed by being either absorbed or scattered. I hope you are absolutely clear about the beam attenuation. Now I am going to show you an experiment medical physicists have performed to show these three possible fates of an X-ray photon beam. It is a classic physics experiment called narrow beam geometry. Some physicists also call it good geometry. Why do we need this experiment? We need it to mathematically prove exactly which photons are physically removed from our treatment beam. Look at the experimental setup on your screen. This is a tissue phantom. This is a source of radiation, suppose our linear accelerator. This is radiation detector. In this experiment, we fire a very narrow stream of X-ray photons. We aim this narrow beam at a very small radiation detector. But notice carefully where we place this detector? We place it at very far away from the tissue phantom. So this detector is very small and kept far away from this tissue phantom. This long distance is extremely important to create this geometry called good geometry. Now look what happens when this narrow X-ray beam enters the tissue phantom. I told you there are three possible things or fates of this X-ray photon beam. First, second, and third. First, look at the blue path on the screen. These are the lucky photons that are transmitted. They go perfectly straight through the tissue without interacting with any atom of tissues and successfully hit this distant detector. This is the first fate. Next, look at the second fate in orange path. These photons crash into an atom and are completely absorbed. Because they stop inside the tissue, they never reach the detector. Finally, look at the purple path. These photons hit an atom and are scattered to the sideways. This is where the long distance becomes extremely important. Because the detector is so small and placed so far away from the phantom, these scattered photons do not reach the detector. Therefore, this entire experimental spatial setup only measures pure transmission. This experiment proves that these three fates of photons, transmission, absorption, and scattering, do not exist in only theory. This happens every single moment when an X-ray photon beam is fired towards patient's body. This brings us to a very clear conclusion. This special narrow beam experiment proves a fundamental rule of medical physics. Only the perfectly straight transmitted photons will ever strike our detector. If a photon is absorbed, it never reaches the detector. If a photon is scattered, the long distance ensures it completely misses out our detector. This proves exactly what beam attenuation truly means in our clinic. Attenuation is simply the measurable physical removal of photons from the primary beam. Once again, attenuation is simply the measurable physical removal of photons from the primary beam. And this removal strictly happens through a combination of absorption and scattering. Understanding this unique experiment helps us believe that these things do happen in real life. Let us quickly summarize the three possible fates of our photon. Look at the summary table on your screen. There are three possible fates of a photon. All these four are the parameters we will compare for these fates. These four parameters are what type of interaction a photon suffers, how much of its energy is lost, what is its trajectory once it enters a tissue, and what is the final status of primary beam. First, we have transmission. Here, there is no interaction with the tissue at all. The photon loses 0% of its energy. It travels in perfectly straight path. Therefore, it is successfully retained in primary beam. We say that the X-ray photon have transmitted. Second, we have absorption. This happens when the photon makes a direct hit with a tissue atom. The photon loses 100% of its energy. its path trajectory is completely terminated. As a result, it is permanently removed from our primary beam. We can say that the X-ray photon is absorbed. Third, we have scattering. This acts just like a glancing blow. See here. The photon loses only a partial amount of its energy. However, its path is strongly deflected away from our target. Because of this deflection, it is also considered removed from the primary beam. This simple table clearly shows why both absorption and scattering actively contribute to total beam attenuation. Now let us move to another topic of our lecture, attenuation coefficient. Listen, we have just learned that X-ray beam gets weaker and weaker as it travels through the patient's body tissue. But we must clearly understand exactly how this weakening of photons actually happens. It does not happen by subtracting a fixed number of photons. Instead, the tissue removes a fixed percentage or fraction of photons. Think of it exactly like a strict tax rate. In the first 1 centimeter of tissue, if the first 1 centimeter of tissue removes 10% of photon, the next 1 centimeter will not remove the exact same number of photons. It will remove 10% of the remaining photon. Once again, if the first 1 centimeter of tissue removes the 10% of the photons, the next 1 centimeter will not remove the exact same number of photons. It will remove 10% of the remaining photons. Because you are always taking a percentage of a smaller remainder, the beam never truly drops to absolute zero. This specific type of continuous percentage reduction is what we call as exponential attenuation. Exponential attenuation. The attenuation is exponential. But how do we accurately measure this exact stopping power for different tissues? Before we move forward, let us quickly define what stopping power actually means. Think of stopping power simply as a material's ability to stop a moving particle. It is strictly defined as the exact rate at which a particle loses its energy over a set distance. It measures exactly how much energy is drained out of that particle for every unit of distance it travels. To do this, we use a very important metric called as attenuation coefficient. Attenuation coefficient. Think of coefficient simply as a strict rate of removal. It tells us exactly what fraction of the X-ray photons will be removed from the beam over a set distance. In medical physics, we have two specific types of attenuation coefficients you must clearly understand. The first one is called the linear attenuation coefficient. Linear attenuation coefficient. You can see it represented on the screen by Greek letter mu. What does this linear attenuation coefficient actually mean? It measures the exact fraction of photons that are removed from the primary beam. And it measures this precise removal over a specific unit of thickness of tissue or matter. In our clinical practice, we usually measure this over a distance of 1 centimeter. Now, this rate of removal is not a single fixed number for every situation. It is strictly controlled by 3 major variables. First, it depends on the energy of your X-ray beam. We know that higher energy beams are much more penetrating. So a higher beam will eventually penetrate more and naturally have a lower rate of removal of photons by the matter it is passing through. Second, it depends on the atomic number of the patient's tissue. Heavy tissues such as bone have a higher atomic number and thus will stop more X-ray photons than soft tissues. Third, it depends on the physical density of the tissue. This means we must look at how tightly the atoms are packed together inside that 1 centimeter volume. Tissues that have their atoms tightly packed will obviously block more photons. But this strict dependence on physical density creates a very interesting clinical problem for physicists. Let us see why density of a material creates a problem. Density of the matter or tissue creates problem. Let us use a simple everyday analogy to understand this density problem. Imagine we have exactly 100 grams of water. 100 grams of water. Now imagine we freeze that exact same 100 grams of water into a solid block of ice. A solid block of ice. If we look closely at the water, its atoms are packed very tightly together. See here. Because of this, higher density water will stop and remove more X-ray photons. We can say water has a higher linear attenuation coefficient. Now let us look at this solid block of ice made up of exactly same 100 grams of water. We know that the ice is less dense, which is why it floats on water. Its atoms are spread much further apart. That means it has lower density. Because of this lower density, ice will remove fewer X-ray photons per centimeter. We can say ice has lower linear attenuation coefficient. This creates a very confusing paradox in radiation physics. Both of these blocks contain the exact same molecules of water, but because of their different densities, they have completely different stopping power. Let us explain you why density of a material creates a problem. This strict dependence on density makes dose calculation very difficult. We have just seen our simple analogy of water and ice. We started with exactly 100 grams of liquid water. We froze it into a solid block of ice. The linear attenuation coefficient changed simply because the density has changed. The ice removes fewer X-ray per centimeter compared to the water. But this is highly confusing and problematic. The atomic recipe has not changed at all. Both blocks are made up of the exact same molecules of water. Now in reality, we cannot simply rely on a coefficient that changes just because the same atoms are packed differently. water and ice. We need another completely pure measurement of stopping power. Pure measurement of stopping power. How can we remove the impact of density to measure stopping power of a matter? We will see how we will solve this exact problem in our next slide. To solve this confusing density problem, we created a second measurement. It is a much more fundamental metric called as mass attenuation coefficient. Mass attenuation coefficient. The earlier was linear attenuation coefficient. This is mass attenuation coefficient. If you look at the formula on your screen, the calculation is very simple. We just take the linear attenuation coefficient and divide it by the density of the material. By mathematically dividing out the density, we get a completely pure measurement. This new mass attenuation coefficient is completely independent of the material's density. Let us go back to our simple analogy of water and ice. Because we mathematically removed the impact of density, this new coefficient is exactly the same for both water and ice. Once again, because we mathematically removed the impact of density, this new coefficient is exactly the same for both water and ice. It does not matter if the water is liquid or frozen solid. This gives us the true fundamental stopping power of a matter. Understanding this pure measurement is absolutely essential for accurate dose calculations in our radiotherapy. Let us now move to the mathematics of attenuation. We have seen the physical interaction of our photon. But how do we actually calculate this in the clinic? We must translate these physical interactions into simple mathematical equation. This is exactly what we will do in this next session. Let us start with a very simple scenario. Imagine we have a monoenergetic beam. This means every single photon in this X-ray photon beam has the exact same energy. When this uniform beam passes through the patient's tissue, its intensity is gradually reduced. But exactly how is this intensity reduced? The answer to this question dictates the fundamental mathematics of our daily radiotherapy. Let us learn it. We must first correct a very common misunderstanding among beginners. Many of you assume that a specific thickness of tissue will always subtract an exact same number of photons. Let us look closely at the calculations on the left side of your screen. This represents linear subtraction. Imagine our primary beam starts with exactly 100 photons. Let us assume that when an X-ray beam passes through this tissue, the first centimeter of tissue subtracts exactly 10 photons. So 100 minus 10 leaves you with 90 photons. Now here is the mistake a beginner make. They think that the next 1 centimeter will subtract exactly 10 photons again. So according to them, 90 minus 10 leaves you with 80 photons. But this simple mathematical assumption is completely wrong in medical physics. The human body does not work like a simple subtraction machine. To understand the reality, let us look at the right side of your screen. We must remember that photon interaction inside the patient are completely random events. Because these atomic collisions are random, the tissue never removes a fixed number of photons from the beam. Instead, the tissue always removes a fixed percentage of the beam. Once again, the tissue always removes a fixed percentage of the beam. We call this specific process exponential subtraction. Exponential subtraction. Let us accurately calculate how this actually works in the clinic. If the first centimeter removes 10% of your 100 photon, it successfully removes 10 photons. Now you are left with exactly 90 photons. But the second centimeter will not remove another 10 photons. It will remove exactly 10% of the remaining 90 photons. 10% of the remaining 90 photons is only 9 photons. So 90 minus 9 leaves you with 81 photons. You're always taking a strict percentage out of a smaller and smaller remainder. Understanding this fundamental difference is the absolute key to master your daily dose calculations. I am going to use a very simple analogy now to explain the exponential removal. I want you to think of beam attenuation exactly like a strict tax rate. Imagine a primary beam starts with exactly 100% of its initial photons. Now imagine the patient's tissue charges a flat tax of 10% for every single centimeter the beam travels. When the beam passes through the very first centimeter, the tissue takes its 10% tax. This means 10% of the photons are physically removed by absorption and scattering. Now you are now left with 90% of your original beam. Until this point, maths is easy. Now the beam travels through the next 1 centimeter of tissue. Here is where you must pay close attention. The tissue does not subtract another flat 10 photons. Rather, it subtracts 10% of the remaining 90%. 10% of remaining 90 is only 9. So 90 minus 9 leaves you with exactly 81%. When the beam travels through the another 1 centimeter, the exact same rule applies. The tissue takes 10% of the remaining 81%. This leaves you with exactly 72.9% of your photons. Notice that you are always taking a strict fixed percentage out of a smaller and smaller remainder. Because of this continuous percentage drop, the beam intensity theoretically never drops to absolute zero. This specific type of continuous mathematical reduction is what we call exponential attenuation. I hope you are clear now. Now let us look at the famous mathematical equation that describes this exact process. This is a tissue. This is the initial intensity of this incident treatment beam. It enters and passes through this tissue. Part of it gets attenuated during its travel within the tissue. This is the final intensity of this beam when it exits the tissue on other side. Now let us see the equation. The equation reads as n of x equals n0 multiplied by e to the power of minus mu. Do not let this mathematical formula intimidate you. Don't get confused. Let us break down these simple terms so that they are very easy to remember for your daily practice. First, look at n of x. This is the final transmitted intensity of the beam after it successfully passes through the patient's tissue. Next, look at n0. This is the initial intensity of our primary beam right before it hits the tissue surface. Then we have letter x. This simply represents the exact physical thickness of the tissue the beam is passing through. And finally, we have the Greek letter mu. We have already studied this in our previous slides. Mu is the linear attenuation coefficient. I want you to think of mu as that exact literal tax rate we just discussed. It dictates the specific percentage rate at which the particular tissue removes X-ray photons. By using this simple equation, we can mathematically predict exactly how much energy will reach the deep tumor. Let us bring all this mathematics back to the physical reality inside our patient. Look at the downward curve on this slide. We started with 100% of our beam. Then it dropped to 90, then 81, and then 72.9. Because the human tissue always takes a strict percentage out of a smaller remainder, the beam intensity never truly drops to absolute zero. It just gets weaker and weaker as it travels deeper into the body. This continuous, never-ending downward curve is exactly what we call exponential attenuation. I want you to pay very close attention to this clinical insight. Mastering this concept of exponential removal is absolutely vital for your career as a radiation oncologist. It is the fundamental key to understanding true beam physics and your daily treatment planning. It helps you predict exactly how much destructive energy will successfully reach the deep tumor. Let us now bring everything together into our one final master framework. First, we have the physical mechanism. We know that our X-ray photons interact with human tissue via absorption and scattering. Second, we have the clinical definition of attenuation. These two specific interactions actively remove photons from our primary treatment beam. This physical removal is exactly what we call beam attenuation. Third, we have the core of mathematics. We learned that this removal does not happen by subtracting a fixed numbers. It happens by removing a fixed percentage of remaining photons, just like a strict tax rate over a fixed distance. This specific percentage removal creates a continuous exponential decay of the beam intensity inside the patient. Mastering this entire framework is your first big step as an radiation oncology resident. It allows you to deeply understand how radiation behaves inside the human tissue. In our next section, we will use this solid foundation to learn about beam quality and beam hardening.